Hi, this is LMRR1502 Photonics Technology for Societal Wellbeing, Teknologi Fotonik untuk Kesejahteraan Masyarakat. So the title of this lecture is Photonic Devices and its Application. I am Associate Professor Dr. P Susthitha Menon from the Institute of Microengineering and Nanoelectronics, IMEN, UKM. So as mentioned, there will be 3 classes for this lecture, Photonic Devices. So we start off with the first class, which is Introduction and Application of Photonic Devices for Societal Wellbeing. Okay, we move on to the introduction slide. What is photonics? Photonics is everything that includes generation, amplification, transmission, modulation, detection, and all those numerous applications where light is used. And photonics is a key enabling technology. It is so ubiquitous in our daily lives that the 21st century has been called the age of the photon. So it covers a wide range of different fields and applications. So what can we do with photonics? So the characteristics of the waves of light or individual photons that make up light can be used to explore the universe, cure diseases, and even solve crimes. And photonic devices are components or chips that are used in various applications that involves light. So for generation of light, we have LED and lasers. Amplification of light, we have semiconductor optical amplifier. Transmission of light, optical waveguides. Modulation of light, optical modulators. Detection of light, photodetector, and solar cells. So in this particular lecture, we will touch on photonic devices that transmit or that generate and also detect light. So mainly on LED and laser, as well as photodetector and solar cells. Okay, so we move on to the electromagnetic spectrum. So the photonics covers the full electromagnetic or EM spectrum from radio waves up until gamma rays, and this includes the X-rays, ultraviolet, UV, and infrared IR light. So as you can see from here, it's the wavelength. These are the names of the waves, and this shows the size of the wavelength, the relative size, the sources of the wavelength, and finally the frequency. Okay, so radio waves have optical wavelengths about 100 meters. It's huge wavelengths, and the size can be equivalent to the size of a soccer field or a house. Huge. Sources can be from a radio transmitter, and the frequency is very high in terms of very low in terms of hertz, 10 to the power of 7 hertz. Okay, so moving on, we go to the microwave. So the wavelength becomes smaller now, 10 to the power of -2 meters, and the size is equivalent to the size of a baseball or even this dot. And the sources can be like from microwave oven, from radar, and as you can see now here, the frequency becomes higher than radio waves. We move on to infrared. So the wavelength becomes smaller, 10 to the power of -5, and it's equivalent in size to a cell. And sources of wavelength such as people, you and I, are sources of infrared emission, and the frequency can range anything from 10 to the power of 13 to 10. So even if we cannot see the entire electromagnetic spectrum, the visible and invisible light waves are a part of our everyday life. So we move on. Just now was infrared in the previous slide. So we have the visible spectrum here. So you can see from the whole spectrum, the visible spectrum takes up only a very small portion of the whole EM spectrum. And moving on, we have ultraviolet. So the equivalent size is somewhere in the size of a virus or a protein. And for visible light, of course, we have the light bulb, something that we can see with our bare eyes. And the frequency is about 10 to the power of 15, 10 to the power of 16 hertz. This is for ultraviolet. Okay. And we move on to smaller wavelengths, X-rays. So the size is equivalent to the size of a protein, a molecule, or even an atom. And sources of X-rays are like X-ray machines, and the frequency becomes much higher now, 10 to the power of 18, 10 to the power of 19 hertz. And last but not least, we have gamma rays. So the wavelength is very, very small now, all right, in size of picometers. And the emission or the sources of gamma rays is from radioactive elements, and you can see that the frequency becomes very, very high, up to 10 to the power of 22 hertz. Okay, so just a short timeline of photonics. At the beginning of the 20th century, Max Planck and later Albert Einstein proposed that light was a wave as well as a particle, which was a very controversial theory at the time. How can light be two completely different things at the same time? Experimentation later confirmed this duality in the nature of light. So we can see here in about 300 BC, Euclid was the first to write about reflection and refraction. And then we have many other famous scientists, Ptolemy Snellius, he's the originator of the Snell's law in 1621. And then you have Euler in 1746, who came up with the wave theory of light refraction and dispersion. Isaac Newton, he wrote a book called Optics in 1704. And Kepler, 1611, how light focuses light, laws of rectilinear propagation of light, and so forth. So Thomas Young performed the Young's experiment, where it shows the wave nature of light and also interference. This was in 1801. Fresnel, the famous Fresnel, who is famous for the Fresnel equation, who showed the diffraction of light wave and also polarization for transverse wave. We also have Poisson. Poisson equation is also a very famous equation currently being used in many photonic based softwares. And then you have J.C. Maxwell, who came up with the theory that light is an electromagnetic wave. So the word photonics actually appeared around 1960, which is when Theodore Maiman first demonstrated the laser. So moving on, you can see over here the laser was discovered in 1960, and just prior to that we have C.H. Downes, who invented the maser. So maser is a microwave amplification. M stands for microwave and L is light amplification. So prior to that we have Einstein, 1905, who came out with the special relativity and also photoelectric effect, and Max Planck, black body radiation. So moving on from 2000 onwards, the emphasis is on nonlinear optics, quantum optics, and also space interferometry. Okay, so just a short timeline of photonics. Nobel Prizes in Photonics. So in 2012, two researchers, Sergei Harochi and David J. Wineland, one from France and the other is from USA, they received the Nobel Prize in Physics for quantum non-demolition measurement. So basically their Nobel Prize is for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So you can see here, these are Rydberg atoms, which are roughly 1,000 times larger than typical atoms. They are sent through the cavity one by one. So this is a cavity, it's like a hole. So they are sent in one by one. At the exit, the atom can reveal the presence or absence of a photon inside the cavity. Okay, and photons bounce back and forth inside a small cavity between two mirrors for more than 1/10 of a second. So before it disappears, the photon will have traveled a distance of 1 trip around the Earth. Okay, so this is called the quantum non-demolition measurement, for which both of them received the Nobel Prize in 2012. Moving on. So in 2014, another Nobel Prize in Physics in the field of photonics for the efficient blue light emitting diode, LED. So 3 researchers, Isamu Akasaki, Hiroshi Amano, and also Shuji Nakamura. So the Nobel Prize is for the invention of efficient blue light emitting diodes, which has enabled bright and energy saving white light sources. So as you can see from here, using phosphorus, the blue or ultraviolet LED can be used to produce white light. At the same time, it can be used in combination with green and also red LEDs to form white light after color mixing optics. Okay, so from blue LED they were able to produce white LED. And finally in 2018, another Nobel Prize in Physics mainly in photonics. So this is for optical tweezers and also high intensity ultra short laser pulses, which we also call chirped pulse amplification. So three researchers, Arthur Ashkin from USA, Gerard Moreau from France, and Donna Strickland from Canada. So their Nobel Prize is for groundbreaking inventions in the field of laser physics. So Dr. Arthur Ashkin, he invented optical tweezers which use pressure from a highly focused laser beam to allow researchers to hold microscopic objects, for example particles, atoms, viruses and other living cells steadily. So using light to hold objects. And these optical tweezers, which allow scientists to control the movement of tiny things, have been especially important in biological research on viruses and other microbes. As for Arthur Ashkin, he becomes the oldest person to win a Nobel Prize, and Dr. Donna Strickland and Gerard Moreau developed a method for generating high-intensity ultra-short laser pulses known as chirped pulse amplification. So these became the standard for high-intensity lasers, for example, those used in millions of corrective eye surgeries every year. We call it LASIK. It's for cataracts removal. Okay, so they did their groundbreaking work in University of Rochester, 1980s. And so you can read further if you're interested to know more. Okay, so this is the third Nobel Prize in photonics. And now let's look at the photonics market worldwide. So it is estimated the revenues for 2020 will reach as high as 334 billion for the photonics market. So this is from 2012 right until 2020. This is the compound annual growth rate, and this is in terms of billions. So you can see it is steadily an increasing trend, and with a high of 334 billion. Photonics market worldwide. This simple figure shows the geography of photonics components production. So nearly 4,300 companies across 53 countries made photonic components in 2018. So that's a huge number. Many companies are involved in photonics. And this shows the top countries for 2018. So this is company count by country and photonics revenue by country. Okay, so this is the income and this is the involvement. So as you can see from here, China, USA, Germany and Japan are the major players for company count, the number of companies which are involved in photonics. In terms of revenue, income, Japan is the highest, followed by USA and also China and Korea. Okay, so they are the highest revenue earners for the photonics field. In terms of photonics market segment, top 5 growth segments based on compound annual growth rates between 2012 and 2020. So you can see here there are many different fields which involves photonics: additive manufacturing, biomedical, consumer and entertainment, defense, displays, lighting, optical communication, semiconductor sensing, and also solar photovoltaics. So the highest increment or growth rate can be seen in solar photovoltaics. Okay, so it has a sharp increase over here, about 25% increase. So China and US continue to drive the global market, but low prices are attracting new countries and expanding the overall market. Defense, safety and security, all right, this is an increment of 12%. Resurgence in defense procurement continues apace as global security threats continue to intensify. Advanced manufacturing, an increase of 11%. So robotics and vision technology are gaining momentum. Implementation of three-dimensional printing, or we call it additive manufacturing, is increasing. Next, we have optical communication, information processing and also storage, an increment of 11%. So the need for global rollout of 5G and the need for photonics in data centers are shaping this market. And last but not least, we have sensing, monitoring and control with an increase of 9%. So the demand for autonomous systems and the Internet of Things are driving demand for a wide variety of photonic sensors. Okay, so the source of this report is from the Optics and Photonics 2020 Industry Report. Okay, next let's look at photonics and Internet of Things, or we call it IoT. So the Internet of Things is the internetworking of physical devices, vehicles, we also refer to them as connected devices and smart devices, buildings and other items embedded with electronics, software, sensors, actuators and network connectivity, which enable these objects to collect and exchange data. So the figure here shows the Li-Fi LED. Okay, so basically you have LED light, two LED lights here, and they act as access points of data. All right, where you have light. Okay, LED normally they have light, but together with the light there is also data. You can see the ones and zeros, they're actually data. And this is another LED light, also light with data. So a point of access, so this is point access 1, this is point access 2, may be shared by several USB keys, and a single USB key may pass from one point of access to another while retaining its connection. So you have a USB key here, it's connected to a computer via USB, and it receives data from the luminaire and re-emits a signal to the point of access via an infrared beam. So it receives the signal and it can transmit back the signal, similar as how a Wi-Fi dongle would work. And Li-Fi enables bidirectional transmission of data with a modulated LED light beam. So the light will be traveling through a power cable and it is connected to a server or a switch for data transmission. Okay, so this is Li-Fi. So what is the difference between Li-Fi versus Wi-Fi? It is not the replacement of Wi-Fi technology. It can be considered as an incredible companion of the Wi-Fi technology. It operates between 380 nanometer to 780 nanometer optical range. And Li-Fi is used to exchange data incredibly rapidly and securely at much lower power level compared to Wi-Fi. So Li-Fi stands for light fidelity, whereas Wi-Fi stands for wireless fidelity. And as you can see here, the applications are in airlines, undersea explorations, operation theaters in the hospital, office and also home premises for data transfer and also internet browsing. Whereas Wi-Fi is normally used for internet browsing with the help of Wi-Fi kiosks or Wi-Fi hotspots. Okay, and Li-Fi is transmits data using light with the help of LED bulbs, whereas Wi-Fi transmit data using radio waves. So this is radio wave, this is light wave, with the help of a Wi-Fi router. Okay, and for Li-Fi it can go up to 1 gigabit per second, and for Wi-Fi as low as 150 megabit per second, but it can go up to 2 gigabit per second. This shows the difference between the different technologies. So we have 1 gig, this was 1G, this was introduced in 1970s, and now we have 5G deployed in 2014-2015. So you can see the bandwidth keep increasing, and it uses different multiplexing techniques for the data, from FDMA, frequency division multiple access, and we move on to time division multiple access, and finally code division multiple access. So CDMA, you also have optical code division multiple access, so the way data is multiplexed and transferred along the fiber transmission system. Okay, so more details about artificial intelligence, 5G and also IoT. So this figure shows the interaction between things, internet and also intelligent, and overlap between internet and things is called Internet of Things, and overlap between things and intelligence creates an intelligent individual, whereas overlap of internet and intelligence creates intelligent internet. Overlap of all three creates the 5G intelligent IoT network. So this is a figure of the network. So as you can see, you have a processing center in the middle, and it is surrounded by the object processor or the base station to collect and receive the information. And in the outer ring here, we have the sensing region to sense various kinds of data. And last but not least, the most outer ring comprises of application. And this application can be in terms of healthcare, in terms of transportation, education, fire station, and so forth. All right, so it is in the most outer ring, and user control happens between the application and also right until the object processor. Okay, that means you send and receive data from here. Okay, and you also have MIMO lines, control link, and also communication link between all these different regions. So this architecture is actually based on 5G cellular network. So it is used to process big data intelligently and optimize the communication channels, and it includes the different regions. IoT forecast, this was taken in 2018. So what you can see here is an increase or a steady increase in IoT devices, both wide area and also short range. Okay, the light green is for short range and the dark green is for wide area. Versus PC, tablet, laptop, and also mobile phones, the increment is quite low as compared to the IoT devices. And you can see in 2022, the CAGR can go up to 30 or 20% for IoT devices. So around 29 billion connected devices are forecasted for 2022, of which around 18 billion will be related to IoT. So it is predicted in due time, mobile phones are expected to be surpassed in numbers by IoT devices, which include connected cars, machines, meters, wearables, and other consumer electronics. The top 10 IoT segments, this was taken from IoT Analytics, January 2018. So it lists here smart city, connected industry, connected building, connected car, smart energy, others, connected health, smart supply chain, smart agriculture, and also smart retail. So you can see here it is divided to the Americas, the Europe, and also Asia Pacific region. So compared to the three regions, yes, Asia Pacific is a bit lower in terms of the share, market segment share, but at the same time, we are in increasing trend. Okay, so the highest of course is in Americas, but we are actually in increasing trend. Okay. There are many different types of IoT devices and sensors, and many, if not almost all, are related to photonics, where you have some like IR optical sensor, LDR sensor, photodiodes, IR proximity sensor, and so forth. So many of the IoT sensors are related to photonics. What is the relation between photonics and Industrial Revolution IR 4.0? So IR 4.0 comprised of an integrated system of automation tool, big data analytics, and also robotic control. The entire system helps in the gathering of data and further integrate it with the digital systems, which help in better functioning and improve efficiency. So Industry 1.0 was using mechanization, steam power, and also weaving loom. This was way back in 1784. We moved on to Industry 2.0, where we have mass productions, assembly lines, and also the introduction of electrical energy. This was in 1870. And after that, about a decade later, in 1969, we had Industry 3.0, which brought about automation, computers, and also electronics. And then today, we are in what we call Industry 4.0, which involves cyber physical systems, Internet of Things, networks, big data, artificial intelligence. So these are all keywords that you must know, should know, because it is here to stay. Okay, so we all know that the world is being hit with COVID-19 pandemic. How is photonics related to COVID-19 pandemic? So this was extracted from a journal. The journal's name is ACS Nano, and it was published this year, very recently in 2020. So this shows the usage of light for detecting COVID-19 virus. And it is actually a dual functional plasmonic biosensor. It combines a plasmonic photothermal effect, which is the light, the laser diode from the top is the photothermal effect, and localized surface plasmon resonance, or LSPR, which was formed from these gold nano islands over here. So again, there is a light here, LED light, which hits the gold nano islands, and light is reflected back. This is what we call plasmonic sensing. So it provides an alternative and promising solution for the clinical COVID-19 diagnosis. So the two-dimensional gold nano island over here, these are all gold nano islands. It is functionalized, which means it has got some attachments on it with complementary DNA receptors, and it can perform a sensitive detection of the selected sequences from severe acute respiratory syndrome coronavirus 2 or SARS-CoV-2 through nucleic acid hybridization. So if you have the COVID virus and it's attached to this functionalized layer, so if someone has got the virus, we can see a difference in the curve of the sensor. So it exhibits high sensitivity towards the selected SARS-CoV-2 sequences with a lower detection limit down to the concentration of 0.22 picomolar. So very small amounts. Even if a little virus is present, the sensor can detect that this person has got the virus or not. And it allows precise detection of the specific target in a multi-gene mixture. So basically you have two lasers. One is a laser from the top, laser diode, and the other laser is a plasmonic sensor over here. Okay, so it passed through many different layers. You have different layers over here, and then light is finally concentrated on the gold nano island, and the reflected light will show whether there is virus present in a person's blood or not. Okay, finally we move on to the technical applications of light. Okay, in technical applications of light, we will cover some basic information about light, production technology, data transfer, image capture and display, medical technology, as well as lighting. Okay. Else than that, we'll also look at traffic, photovoltaics or solar cell, the environment, research and economy, and also how does the photonics enthusiast used all the different technology from light in his daily life. Okay, so this was taken from the SPIE Photonics in Infographics. Okay, so we move on to the basics first. What is photonics? So as mentioned, photonics is the generation, transmission and utilization of light and other electromagnetic radiation. Photonics offers solutions to the global challenges of our time. Okay, so generation, transmission and also utilization. Smallest points. Light can be focused on extremely small diameters. So you know the size of a paperclip wire is about 1000 micrometers or 1 millimeter. Okay, that's the size of a paperclip wire, its diameter. Moving on, you have a pin. The size of a pin, the edge of the pin is 500 microns, which is 0.5 millimeter. We go smaller. Focus in laser cutting. When you're using a laser cutting, what is the focal point? It's 100 micrometer, smaller. Your hair, human hair, is 50 micrometer. That's how small it is, one hair. And you know, in photonics, the optical fiber core, it is 10 microns thick. Okay, this part over here which carries the optical signal is 10 microns thick. That means you take one hair and you cut it into 5 small pieces. One small piece represents one fiber optic core. That is how small signals are transmitted in fiber optic systems. Okay. Highest velocity, it has got the highest speed. Nothing is faster than light. The speed of light is approximately 3 times 10 to the power of 8 meter per second. Now, how far does a message travel in 1 second? Let's look at different methods of sending a message. If you use foot, that means you walk, the message can travel 1.5 meters in 1 second. If you're using a pigeon, or we call it a carrier pigeon, it can travel 20 meters in 1 second. If you're using an aircraft, it can travel 250 meters in a second. An Apollo moon rocket, it will travel 10 kilometers in 1 second. But what about an optical fiber cable? In 1 second, the message can travel 200,000 kilometers, which is equivalent to 5 times around the Earth in an optical fiber cable. And light in space is even faster. In 1 second, light in space can travel 300,000 kilometers. And the distance between Earth and also Moon, it is 384,000 kilometers, just for comparison purposes. So that's how fast light can travel in space. So it's very, very fast. Shortest time. Light makes even the fastest events measurable. How long does it take to blink an eye? 1 second. How long does it take for an athlete in action? 1 millisecond. A high-speed camera? 1 microsecond. Electric impulses in a computer? 1 nanosecond. But there are things which are happening in the world which takes a shorter time than all this. For example, we have chemical processing such as the splitting of DNA. It takes 1 picoseconds. The processes inside an atom, how electron circulates around the nucleus in an atom, it is 1 femtosecond. And last but not least, you have 1 attosecond. So all these events which happen very fast can only be measured with light. Highest power. With the pulse operation of lasers, a power orders of magnitude greater than anything we have known so far can be achieved. This is made possible through the concentration of laser power to very short femtosecond pulses. So let's compare two types of power. This is worldwide power generated by electric power plants, 2.6 terawatts or 2600 gigawatts. Okay, and over here is a Berkeley Lab laser accelerometer. So do you know how much power is generated by this laser? 1 petawatt, which is equivalent to 1 million gigawatts. Okay, so you can compare 2600 gigawatts. This is worldwide power generated by electric power plants versus the laser, 1 million gigawatts. And this shows the spectrum of the laser. So it has a laser pulse width of 40 femtoseconds, and the peak powers are reached periodically for very short time intervals. So it's just 1 second. So 1 laser pulse, after 1 second, another laser pulse, after 1 second, another laser pulse. Each laser pulse is 1 million gigawatts in terms of power. So very high energy and very fast laser pulses. Undisturbed superposition. So dozens of data signals can be coupled into one single optical fiber and be separated again at the receiver's end. The signals can be very finely distinguished based on their wavelength, which is the spectral color, polarization, and also the phase. So you have the sender here, you transmit some kind of signal. So you will use different wavelengths. Some will use the blue, some will use the green, some will use the yellow, some will use the red. All of them will be multiplexed and they be sent through an optical fiber link. In this optical fiber link, there are over 40 channels with data signals, and they can be superimposed on one fiber. And the transmission rate is 100 gigabit per second. So over here is the receiver. So whoever they are sending to receives it back in the original wavelength. So this is called wavelength transmission of optical signals. Light spectrum. Light is the very small part of the electromagnetic spectrum, and it's visible to the human eye in the wavelength range of 380 to 780. So you can only see these colors, which is the visible region. But actually, you know, in sunlight, they have so many other spectrum. This is the spectrum of the sunlight on Earth. So the eye can only see very small amounts of ultraviolet light, but actually it's a huge, quite huge chunk from the sunlight. Okay. So the hidden realm of photonics. So photonics applications use a broad portion of the electromagnetic spectrum that is predominantly not visible to humans. So you can see here in nuclear technology, cosmic radiation, and moving on to gamma radiation, X-ray, ultraviolet, and also infrared. So you have radiocarbon dating for using cosmic radiation, and for gamma radiation it's used mainly for material testing. It is in 1 zeta hertz frequency. The wavelength is 1 picometer. X-ray, the wavelength is 1 nanometer. The frequency is 1 exahertz. So you can see here the frequency is becoming longer and longer. All right, and it's used in X-ray machines. So ultraviolet, you use ultraviolet lamps also to look at money. All right, if you have stolen money and so forth. Visible light is what you can see with your eyes. So all this cannot be seen with your eyes. You only can see this portion over here. You have for infrared, heat lamp. In the terahertz, you have the full body scanner, the application. Microwave, you have your cell phone network and also the wireless local area network, LAN. Radio waves are used in RFID for identification system in your cards and so forth. Also in television. And finally, AC current or alternating currents, you use it in the power line. We call it the long wave, right? So from shorter wavelengths to longer wavelengths, equivalent to high frequencies to low frequency over here. So microwaves are also used for radar, and radio waves are also used for broadcasting. So you can see the application of photonics is over here, and electronics are mainly over here. And this is for nuclear technology. Alright, shorter wavelengths. Wavelength has a great influence on the performance of optical systems. Shorter wavelengths can produce smaller focus diameters, making greater recording densities possible on optical storage media. So these are comparison of 3 different types of storage. This is a CD, a compact disc, a DVD, and a Blu-ray disc. Alright, so you can see the different types of lasers used. This uses an infrared laser which is at 780 nanometers. This uses a red laser which is at 650 nanometers, and this uses a violet laser at 405 nanometers. And you can see, since the wavelength is huge, the focus point is also huge over here, and the amount of data that can be recorded is small. So as the wavelength becomes smaller, you can see that the focal point becomes smaller, the beam width becomes smaller, so therefore more data can be recorded into the optical storage media. So shorter wavelengths give a higher optical storage media. So window glass versus optical fiber. Glass is the most important component of optical systems. However, common window glass and glass used in photonics applications are worlds apart. Now let's look at light transmission of glass. How thick can different glass types be so that 1% of the emitted light is still transmitted? This is a window glass, an optical glass, and also an optical fiber. So light is transmitted in all 3 different mediums, and we only want 1% of light of the emitted light is still transmitted. So if you transmit the light in a window glass with a thickness of you can see that 1% of light is only transmitted, okay, for 80 cms only, okay. And in an optical glass, 1% of light is transmitted in an optical glass as thick as 29 meters, okay. And in an optical fiber, in order to obtain the 1% of the emitted light, the optical fiber can be 100 kilometers thick, so very thick, or very far. The light can transmit very far just for 1% of the light to still be transmitted. That means you send here, after 100 kilometers you still can receive. For an optical glass, you transmit here, after 29 meters you can receive 1%. For a window glass, after 80 cms, you can get back 1% of the light. So this is very thin, okay, using a window glass versus an optical fiber. Mirrors versus laser mirrors. Many optical components can be found in their basic forms in the home. The components used in photonics, however, are characterized by the highest accuracy and technical finesse. So this shows a household mirror. Basically, you have a glass plate, you have a back silver coating, and also a protective layer. And what happens is light which is transmitted, 86% of the light is reflected back in a household mirror. In a laser mirror, however, what we have are layers of varying materials. So these materials have different refractive index, and sometimes we can have from 20 to 50 layers, and each layer is about 100 to 200 nanometers thick. So they are applied on the front of the substrate, and what we get is a very high reflectance, 99.9% reflectance, versus a normal household mirror you'll only get 86% reflectance. And in a laser mirror, in a kinetic mount, all right, so its laser mirrors are used in a kinetic mount to get a very high reflectance. Laser types. Lasers are the central component of many photonics applications. The numerous laser types always consist of the same basic elements, although their shape strongly varies. So basic elements are, you have the active medium. The active medium basically is an excited atom or a molecule. And then you have the energy supply, or we call it a pump. It can either be an optical pump, which is based on light, or it can be an electrical pump, which is a source of voltage or current. And then you have the resonator in green. Resonator means end mirror and also the output coupler, where light will oscillate between the resonators. It's like a mirror, so two mirrors for light oscillation to occur. And finally, the red color shows the laser beam. So over here we have the diode laser, the fiber laser, the disc laser, and also the gas laser. So in a diode laser, you can see that the active medium is the one in yellow, and then this is the energy supply is in electrical, light purple, and the resonator, you can see the one in green. So light basically resonates here, and when it gains enough power, it is emitted out as a laser beam. In a fiber laser, the active medium is embedded in the optical fiber, and you have the energy supply is actually optical base, dark purple, and the laser beam goes through this medium, the active medium, and it's emitted out as a laser beam. In a disc layer, is in the form of a chip. So you have the active medium over here, and the energy supply is basically optical, and you have the resonator, two resonators to resonate the light, and finally light is emitted out as a laser beam. In a gas laser, the active medium is in the form of a gas inside this tube over here, and the energy supply is electrical. You supply voltage, you switch on the switch or whatever, you apply voltage, and the resonators you can see in green. So photons will resonate between these two mirrors, and light is emitted out as a laser beam. So 4 different types of laser. Now let's compare the laser with the sun. While conventional light sources emit their energy in all directions, lasers can bundle the emitted light very efficiently into almost parallel light beams of very small diameters. Now let's do a performance comparison between the sun and also a 5 milliwatt laser pointer. So you have the sun, the amount of energy is 174 petawatts, and it reaches the earth. When it reaches to earth, the solar radiation intensity on the earth is about 700 watts per meter squared. This is during the Central European summer. And if you take this solar radiation and you put it through a buttonhole with a diameter of 1.5 millimeters, the performance is about 1 in milliwatt. You get back 1 milliwatt of power. versus this 5 milliwatt of laser pointer. All right, and it is a 1.5 millimeter beam diameter, the size of the laser. Okay, this is the laser, the size of it is 1.5 millimeter in diameter, and if you put it through a buttonhole with a diameter of 1.5 mm, you get back 5. So you put in 5, you get back 5. This is for a laser pointer. Versus the sun, you have 174 petawatts and you get only 1 milliwatt, simply because a lot of scattering and losses occurs along the path. So anyway, lasers, they can bundle the emitted light very efficiently in small diameters.